Okay, well, hello. Good morning from Colorado, where we've got some nice fresh snow on the ground here today. Uh, this is Kevin Cooney. I'm presenting today a little bit on integrated evaluation for the energy transition as part of the energy evaluation series. Um, First, I'll give you just a brief background on myself. I have a small consultancy here in the States called Buca Energy Strategies, where I do work for investors, government agencies, and utilities, amongst others, looking at clean energy and energy efficiency and demand side activities generally. I do serve on the board of trustees for the Energy Evaluation Organization globally. And I also serve locally on the board of directors for my local co-op power association and the Tri-State Generation and Transmission Organization, which the local electric cooperative is part of. I did previously serve as a managing director at Navigant and have a background as an engineer doing research and utility consulting over the last 30 years or so. So today, it's pretty interesting times what's going on in energy. You know, we all talk about the energy transition or clean energy transition. In the US, people are talking about the Green New Deal and various names to things, but the world is changing. There's certainly an increased focus on greenhouse gas reductions, and as a driver in our energy decisions, we know we need to clean up energy supply to reduce greenhouse gas emissions. And one of the other big changes that's happened just in the last couple of years, or I can say, is that renewable generation, solar and wind primarily, are now often the lowest cost of electricity resource on the supply side, displacing many of the fossil fuel resources that we've come to rely on over the last some 70, 80 years and around the world. We need to make some changes quickly based on that. We also see on the demand side that energy efficiency technologies have matured rapidly in the last 10 years. User acceptance for things like LED lighting have grown, for all sorts of other technologies, whether it be heating and cooling technologies, industrial technologies, or others. And so that change is happening very quickly. Supply and demand resources can now interact. I think this is something we thought for many years might be happening, but now we can really do this in computing power, high-speed internet, and inexpensive sensors that allow for extensive data collection and data analytics means that there's no longer a need for demand resources to only be on the receiving end of our electricity. We can actually interact and make changes to the way the system works. And then this last one's really important. Investment life cycles are shrinking. As we look at the traditional electric power system, life cycles sometimes would be 40, 50 years for a power plant that would get built into planning cycles. And as technology accelerates and new technologies keep coming year after year, we can't necessarily afford to be thinking 40 years out and what technologies might be available if something takes that long to pay for itself. So these accelerated changes always make long-term investments challenging, and now it does create an opportunity for us as these new technologies are moving quickly. I'm going to just talk about a couple of key trends. Traditionally in evaluation, we've focused on energy efficiency and some other demand side resources. These demand side or distributed energy resources, as many are now referred to, or include energy efficiency and demand response, but also distributed generation, rooftop solar and the like, as well as battery storage and other types of storage that are coming out of research labs. But battery storage is becoming cost effective in the same way that solar has, and it will drive significant change. We'll get to that in a couple minutes. The other big trend is a bit of a buzz term these days, beneficial electrification. So what does that really mean? how can using more electricity be beneficial when we've been working to use less electricity through energy efficiency for years? Energy efficiency was often assessed on its annual value, how much energy saved, and we could convert that into how many kilowatt hours didn't have to be made on an annual basis. And as always, the cheapest and cleanest kilowatt hour is the one you don't use. Yet at the same time, there are new technologies, electric vehicles, that can displace fossil fuel. And thus, if the source of electricity for charging something like an electric vehicle or for heat pumps in a home that are all electric, if the source of that electricity is cleaner, renewable, then the overall greenhouse gases emitted are much less. And so we see this as beneficial if the cost is reduced, the environment is benefited, less emissions, less greenhouse gas, and also it creates a more efficient grid. We don't have to build out additional infrastructure just for times of peak demand. And we'll get to that as we think about electricity doesn't have the same value all times of day or all times of year. The rates that many people use don't take that into account. So we may, some rate design is being heavily discussed in the US. And rate design is incredibly important to how people use electricity. Just like if you want to fly in an airplane at peak time, you'll pay more than if you want to take the old red eye in the middle of the night. The other thing that's a big trend is people are now recognizing more, policymakers are recognizing the multiple impacts, the benefits of energy efficiency. And I tend to use the word impacts as opposed to benefits because impacts can be both positive or negative, and as an objective evaluator, one must always step back and think that there could be positive or negative connotations for anytime energy efficiency or other technologies are invested in. And we want to keep both of those in mind. So, well, what is evaluation's role in this energy transition? Evaluation we think of as happening during the planning phase and often after the end period of a program or policy. Programs are typically funded to provide incentives for people to utilize more efficient technology. We want to document the impacts of those, whether they be pilot programs, new technologies, new ways of altering consumption behavior of electricity. And so we use that documenting of the impacts and how people utilize electricity, how it fits into their life, what other benefits, those multiple impacts that could be better health from less drafty homes if we insulate or put in new windows, higher level of comfort and ability to use more light in developing countries if we reduce the electric needs to use lights. Those are all multiple impacts that others have talked about in other parts of the series. But we can understand and improve both program and policy performance if we take those findings into account. And then, of course, that can play into energy resource planning for the future. And I'll make the case today that is both supply side planning and demand side planning in an integrated manner. Whether we call it integrated resource planning or we call it something else, we do plan when investments are made for various potential futures. I guess one of the things we want to talk about is how does the time of day when electricity is used impact the environmental benefits? And I'm going to pop up real quickly something that many of you may be familiar with. We call it the duck curve. I think you can see from the shape. This one's from the California Independent System Operator, who runs the wholesale power markets in the state of California. What we really see here is net load, which means the lines which have changed each year with the belly of the duck getting much deeper. That means in the middle of the day when the increased rooftop solar and large scale solar penetration is much higher, then the consumption tends to be in the middle of the day. The need for generation, other forms of generation, goes down. And then later in the day, as the sun starts to get lower in the sky, there's an increased ramp, and oftentimes today, that ramp is filled by natural gas-fired power plants that ramp up quickly to meet the evening demand. While this isn't true in every geography, we're seeing, we would see a different shape to a curve if it was nighttime wind was the potential over generation we faced. So when do you want to use beneficial electrification? Well, we know that if we utilize demand response and distributed resources during this increased ramp time, we don't have as much need to fire up those fossil fuel power plants. And so there's a high value to certain resources during that ramp. And we might want to use the time when we're producing a lot of electricity, whether that be noon when the solar is high, or nighttime when the wind may be blowing strongly in the North Sea, for example. We certainly want to use our charging stations for our electric vehicles. We may want to charge up batteries at a home system or other types of storage, whether they be pumped hydro for large scale or other needs, to utilize that electricity while we have more than we might need at a given time. To move it on a little bit, I'm going to pull up something from some work myself and some colleagues did some years ago, thinking about investments in the grid and what really is a smart grid. It was certainly a buzz term a few years ago. And I think this diagram is interesting to consider, that when new technologies come about, whether they be grid technologies or whether they be energy efficiency technologies or new data analytics devices or data gathering devices, we typically see things happening and maturing in a couple of ways. Early on, there's initiating and exploring phase where we may be looking at testing of new technologies. Do they work as claimed? We might want to conduct some technical or policy evaluation. What are the economics of the new technology look like, and where can they best be deployed? And we saw this happen over the years with more and more efficient refrigeration equipment, with more efficient lighting, as well as many grid technologies that help manage the grid and monitor the grid better, like synchrophasers and things. This led to a phase of functional investing, which has been going on in replacing technologies. Typically, this is what programs often do, one by one. We support a given type of heating and cooling technology or a particular type of lighting. And those investments bring down the cost. And then I'd say probably where we are now is maybe this integrating of cross-functionality as we look at these distributed energy resources and how they can integrate with the grid through these modernized controls and ability to respond quickly and be aggregated. We're at this, getting to functional scale and I'd say early integration. We certainly aren't yet at a fully optimized grid with full deployment of all optimal technologies. That will be some time to come, and maybe this timeline was a big optimistic back in 2009 and 10. So let's take a look now at some specific evaluation analyses of distributed energy resources. We know about level one. Level one is what we've typically done, is assess one type of distributed energy resource in isolation from other types, and typically relative to a static set of resources. And that static set of resources might be, again, to use a simple example, change out of lighting, which reduces overall electric consumption and will also reduce peak demand. We know how to do this. There are plenty of data collection and analysis techniques, attribution discussions, all kinds of things regarding the adoption of individual technologies compared to those that they're displacing. The next level is, assessing more than one type of DER at the same time, and there may be static or dynamic alternative resources. An example here, if we look to the right, we can see that we've got energy efficiency, demand response, and distributed storage as examples of more than one type of uh, resource, which can be combined into what I might call an asset group. And those can be compared to the cost of alternatives, which might mean, which could be doing nothing, paying more, or it could be the alternative, could be a supply side power plant that is considering to be built, or an upgrade to the grid system to create greater capacity on the grid to supply for growth of demand as population increases, et cetera. Level 3 is where it gets complicated. We get to more complexity here. We have to be able to look at these multiple resources and how they interact with each other. Like, there may be interactions that are detrimental when we, I'll use the simple lighting example again. When we change out lighting to lights that don't produce as much heat, we can also reduce cooling load, which is a benefit in warm, hot climates. On the other hand, if that heat was going into the space in a cold climate, more heating will be needed when we make a retrofit for more efficient lighting. So alternative resources can have multiple impacts. And as we look at the interactions of resources on the grid, the ramp time for power plants, the cost for those utility scale resources, as well as the cost to operate, and any uncertainty around, say, how much solar power might be available at any given hour of the day. We fall into the need for lots of data and complex modeling that looks at the interactions amongst these resources. But again, the tools for the evaluator start out with the same basics. We want to measure what's happening at, for each technology. We want to analyze the data and any cross impacts of that. And then we want to look at consider the multiple impacts that may create other benefits on the grid system or for end users that may not have been there before we integrated more than one set of technologies. This I'm not going to spend time on, but it's an interesting forward look. And as we know, planning is forward looking. We have some forward looking evaluation. I would make the case that for evaluation must have some retrospective data collected to validate any forward looking models on expected energy efficiency savings. Same thing would be true if we look at installation of interactive technologies. And we looked at this in a grid area managed by a client, and we grouped families of technology in areas such as transmission and distribution optimization. We looked at grid reliability investments, dynamic and responsive demand, and bundles of technologies that could do that. And what we found is, as we looked at those investments in their life cycle, whether they had 10-year life cycles or 30-year life cycles, we found different kind of payback, if you will. These are projected. Again, this requires going back and doing retrospective evaluation. But we find that things like T&D optimization and grid reliability and dynamic response, demand response, have much higher present value from an investment standpoint than some of the other utility operational efficiencies, or at the time this analysis was done, grid storage integration. Now these have moved. I want to note that this is a dated set of analyses with a set of technologies that may already have been exceeded by today's best available technology and their costs and benefits. But the integration allows for different functions than would be allowed with only one technology. That is really a key. We know that the demand response reduces peak load, reduces line losses. At the same time, it requires investments in automated meter infrastructure, data management systems, et cetera. So it's a challenge, and there's complexity in considering all the costs and benefits with a given technology implementation. And then lastly, I'd just like to quickly note that there are impacts on people and processes. Those are, and this diagram is really looking at the business side. If we think about utility, but it could be applied, the slice that's pulled out here, the billing example inside an electricity supplier is just one example. The idea of this sort of layer cake approach is that we build from the inside out. You first need the base technologies. So you have to have networks, sensors and devices, and those base technologies allow information to be gathered. Databases and documents can be built on these technologies, and then applications, of course, require data and maybe enterprise software that works across organizations. And then social accommodation, I'll talk briefly about, but these are important things to look at the impacts of, both in terms of positive impacts and potential re-engineering required on the business side of things. The billing slice, we know that we have meters that collect usage data for electricity, servers, the hardware to transmit that meter data that then goes into databases and is used on our enterprise resource software and our billing systems. Then the billing systems, of course, need to interact with real people and the way that people go about their jobs, customer service reps, how they interact with customers, what information they can provide, how this new data helps them do their job better and really provide significant support to the technology changes that are happening. So I think we as evaluators need to really consider these kinds of interactions, not just on the consumer end, but on the system end, if we will, if we are really going to combine technologies and see them work in these interactive manner. And to wrap up today, I just want to note, like, the Energy Evaluation Organization, which I'm honored to be part of, and I get to interact with many thought leaders around the world, and in addition to North America, has been working to grow a worldwide community of qualified evaluators. And this is, we often look at evaluating energy policies and investments, as well as programs that might be run by utilities. And that involves sharing of best practices, promulgating consistent protocols, so that we can compare country to country, location to location, in terms of, what are we doing in terms of emissions reductions, and that time value of when the electricity is used will impact how much carbon's in each kilowatt hour, based on what's being put on the grid at a given time. So we do need consistent methods, and we do need to take into account these interactive effects. And the Energy Evaluation Association organization is really in a good position through conferences, through webinars, and sharing of these knowledges to really improve practice around the world. And I would say one of the other roles the organization has is to assure that policymakers have the tools they need to really get feedback on triple bottom line evaluation. And that, again, being applied both to distributed resources and centralized resources, traditional, unidirectional power flows from the big power plants. Those investments need to be assessed as well on the basis of how do they impact the environment? How do they impact the economics of both the supplier and the user? And how do they impact social equity? That's incredibly important in today's world, and access to clean electricity should be a right for every human on the planet. Thanks.